In this video, we will discuss the solutions of the midterm exam on probability and statistics taught in spring semester 2018. The exam contains two parts. The first part contains 10 questions where students answer the questions quickly and briefly explain their solutions. And the second part contains 6 problems. We'll go through all the questions first of all, and we'll discuss them and their solutions in more details later. So the first 4 questions are about different various distributions. Question number 5 is about the standard normal distribution and the normal distribution. Question number 6 about the sets and the complements of the sets and probabilities of those kind of sets. Question number 7 is calculating the simple probabilities. Question number 8 is about the expected value. And question number 9 and 10 are about the combinatorial analysis and counting principles. The first problem on the second section is about the binomial distribution. Students also need to know the law of total probabilities and the multiplication rule. Question number 2 is again about the law of total probabilities and the law of multiplication and the addition of the probabilities. Question number 3 is a little bit difficult. So we're given the random variable, the continuous random variable was a density function, and the students need to work with this density function in order to calculate different features of this random variable. Question number 4 is about the discrete random variable. In this case, we're given the random variable with the probability mass function, and students are required to calculate the expected value of this random variable and the expected value of some function of this random variable. Question number 5 is about the exponential distribution and the Poisson distribution and their connections. Question number 6 is about the properties of the expected values and the variances. So let's go through all the problems now. So in the first problem, we're given the random variable, which is the number of the times you need to shoot until you will get a basket, right? So this is the number of the trials until you will get a first success, and we can use the geometric distribution for this random variable. Question number 2 is the number of the accidents in one day, right? So we can consider the random variable x as the number of the successful trials in one, or number of the events happening during one interval of the time. So in order to calculate the probabilities in this case, we need to use the Poisson distribution. Question number 3 is we roll a die and we consider this trial as successful if we get a 3, right? So x in our case is number of the successful trials, number of the 3s when we roll this die 100 times, right? So this might take the values 0, 1, 2, and so on until 100. Basically, it means that you roll a die 100 times and you never get 3. Or you roll a die 100 times and once you got a 3. And so on, you roll a die and in all the 100 times you've got a 3. So in order to calculate the probabilities, we need to use the binomial formula. And question number 4 is about the number of the people which we have to interview before we'll find the 6th left-handed person, right? So we need x in our case is the number of the interviews, right? So until we'll get the 6th left-handed person. So this can be considered as the number of the trials until we'll get the 6 successful trials. And in order to calculate the probabilities for this random variable, we need to use the negative binomial distribution. Question number 5 is we're given the random variable with the normal distribution, it was the mean 10 and the standard deviation 3. We need to calculate the standard score for the x, which is equal to the 5. So in order to calculate this, we need to use the formula. Z is equal to the x minus mu divided to the sigma, which is 5 minus 10 divided to the 3, which will be minus 5 over 3. And the question number 6, we're given the probability of A, and the probability of the complement of this event is equal to the 1 minus probability of the A, which will be equal to the 1 minus 0.4 or 0.6 simply. And question number 7, we need to evaluate simple probability. We've got a box with 12 chips with different colors. We need to find the probability of choosing one ball, choosing one white chip. So this is the number of the chips, number of the white chips in the box, which is 4, divided to the total number of the chips in this box, which is 12, or basically this will be 1/3. So probability of choosing one ball, one chip, and this will be a white chip, is 1/3. In problem number 8, we're given the random variable which takes the two values, right? So either it takes the 1, either it takes the 2, and what's the corresponding probabilities? Either 0.7 or 0.3. So mean is nothing else as the expected value of this random variable is calculated by multiplying each output to its corresponding probability and summing this at the end. So if we calculate this, we'll get 0.7 plus 0.6, which is 1/3. And question number 9, we've got a 5 books, right? So let's number them 1, 2, 3, 4, 5, and we can put them in the shelf in different orders, right? So we need to figure out the number of the permutations of the 5 different items, basically. So in the first place, you can put the first book, or the second book, or the third book, or the fourth, or the fifth book, 5 different books. But once you choose one of the books on the first place, you cannot choose the same book again on the second, right? So you can choose one of the 4 books, second, third, fourth, or fifth books. So on the first place, we've got 5 options. On the second place, we've got 4 options. On the third, 3 options, 2 options, and 1 option. So the number of the permutations of the 5 different objects is equal to the 5 factorials. And the question number 10 is about the number of the handshakes of the 15 people, right? So we can solve this problem in 2 different ways. So the first person shakes the hands of the 15 people, right? And we'll just eliminate him. And the second person shakes the hands of the rest of the 14 people. The first person shakes the hands of the 14 people. Then the second person shakes the hands of the 13 people. And the third shakes the hands of the 12, and so on. And the number of the handshakes will be 14 plus 13 plus 12, and so on plus 1. So this is the sum the sum of the series is equal to the 14 multiplied to the 15 divided to the 2, or simply 7 multiplied to the 15. Or we can solve this differently by making the pairs, right? So I've got a 2 place, right? So where 2 persons will come there and shake their hands. Okay, so I can choose the first person here and the second person as a second place, right? Or for example, second and the third, or third and the fourth. Please note that the 2 and 1 are considered the same, right? So the number of the choosing the 2 persons out of 15, 2 different persons out of 15 different, is the combination of 2 out of 15, which will be 15 factorials divided to the 13 factorials multiplied to the 2 factorials. So this will be equal to the 14 multiplied to the 15 divided to the 2, or simply again 7 multiplied to the 15. So this is all the questions of the first part. Let's go to the problems of the second part. So in the first problem, the student is taking the multiple choice question. Probability that he knows the answer is equal to the 0.65. So if he knows the answer, so he will answer correctly, answer 100%. And if he doesn't know the answer, he needs to guess this, right? So probability that he doesn't know is equal to the 0.35, right? So if he doesn't know the answer, he needs to guess among the 4 answer choices. So we need to first of all evaluate the probability of answering correctly, right? So let's assume the student is answering some number of the questions, the first question, the second question, and so on. Nth question. So we would like to know what is the expected number of the questions student will answer. So this is kind of like in each of the questions there is a probability of answering correctly or answering wrongly, right? And then we need to calculate the expected number of successful trials, kind of, right? So in order to do this, first of all, we need to calculate the probability of success in every question, right? Which is probability of success in every question is the probability of answering correctly to each question, right? So the student can answer correctly to each of the question. Either he knows this, multiplied to the probability of knowing the answer, plus the student can answer correctly to the question if he doesn't know the answer, right? Multiply it as the probability of not knowing the answer. So this is equal to probability of answering correctly to the known answer, known question is 1, multiplied to the probability of knowing the answer is 0.65, plus probability of answering correctly to the question where the student doesn't know the answer is 1 over 4, because there are 4 options of the question, multiplied to the probability of doesn't knowing the answer, which is 0.35, right? So the answer will be equal to 73, 0.73, and 73.75, right? So roughly 0.74. This is the probability of answering correctly to each of the question, or probability of success. Then the expected value or expected number of the questions will be answered correctly is simply n multiplied to the p, right? Or in this case, we don't know how many questions were given in the question number 1. So the total percentage of the correct answers will be equal to the 74%, right? Basically, so we need to divide the number of correct answers to the number of the questions, which will be simply p multiplied to the 100, right? P. So this is the percentage of the correct answers, or the expected percentage of the correct answers. And the question number 2, the student, we need to evaluate the probability. So let's assume that x is the random variable, is the number of correct answers, right? So in order to calculate the probability of x having different values, we need to use the binomial formula, right? So in this question, we need to evaluate probability of answering 90% of the questions if the number of the questions is 15, right? So 90% of the 15 is 13.45, right? So 0.9 of 15 is 13.5. So in order to answer 90% or more of the questions correctly, so we need to evaluate the probability of answering 14 questions correctly, or probability of answering 15 questions correctly, right? In order to answer 14 questions correctly, probability of this is using the binomial formula 15, 14, multiplied to the p in the power of 14, q in the power of 1, plus combination of the 15, 0, at 15 and 15. Probability of success is 15. Probability of failure is the number of the failures is equal to the 0. And the question number C, so C part is what is the probability that you will get a correct answer to the first five questions in a row, right? So if we've got 5 questions, we need to answer the first question correctly, the second question correctly, the third question correctly, fourth question correctly, and the fifth question correctly. So probability of answering correctly for each of the trials is p, so this will be p in the power of 5 simply. Let's go to the question number 2. In a question number 2, we've got 3 different kinds. So let's say first kind, second kind, and the third kind, right? So probability of having tails for the first coil is equal to the 0.5. Heads. So probability of having heads for the second kind is 0.6. Probability of having heads for the third kind is 0.1, right? So now we need to evaluate. So if we choose one of the kinds randomly, this kind or this kind or this kind randomly, and if we flip this coin, what is the probability of having heads, tails, and tails, right? So what we need to do is we need to evaluate probability of having heads, tails, tails for the first kind, for the second kind, and for the third kind. Then using the law of total probabilities, we need to evaluate the probability of having heads, tails, tails for any of the randomly chosen kind, right? So this is probability of choosing, tossing head, tail, tail for the first kind, multiplied to the probability of choosing the first kind, plus probability of having heads, tails, tails for the second kind, multiplied to the probability of choosing the second kind, plus probability of having heads, tails, tails for the third kind, multiplied to the probability of choosing the third kind. So probability of having heads, tails, tails for the first kind is 1 over 2 multiplied to 1 over 2 multiplied to 1 over 2. And probability of choosing the first kind is 1 over 3. Plus probability of having heads for the second kind is 0.6 multiplied to the probability of having tails is 0.4 multiplied to the 0.4 multiplied to the probability of having choosing the second kind is 1 over 3 plus probability of having heads for the third kind is 0.1, probability of having tails is 0.9 multiplied to the 0.9 multiplied to the probability of choosing the third kind is 1 over 3 again, right? Probability of tossing the coins is head, tails, tails, exactly in this order. For any kind which we choose randomly is equal to this number, to this big number. So on the B part, we need to calculate the probability using the Bayes law. So assuming that we've got the head, tails, tails, so we chose one of the kinds, we toss this, and we've got exactly head, tails, and tails. What is the probability that we've chosen the fair kind, the first kind, right? So in order to calculate this, we need to use the Bayes rule. So in order to calculate this, the Bayes rule was like probability of head, tails, tails for the first kind multiplied to the probability of choosing the first kind divided to the probability of head, tails, tails, right? So probability of getting head, tails, tails exactly in this order for the first kind is 1 over 8, right? 1 over 2 multiplied to the 1 over 2 multiplied to the 1 over 2. Multiplied to the choosing the first kind is 1 over 3. We need to divide this to this number, which is probability of tossing any kind as in this order, head, tails, tails, and evaluate this probability like this. Question number 3 is about the continuous distribution. So we're given the random variable x with the density function, and in this density function there is a parameter k. We need to get rid of this k first of all. So basically we need to find a k so that this density function will be the proper one, right? So we know from the properties of the density function that the total area under the density function should be equal to the 1, right? So the density function has the values between 0 and 3, and it doesn't have the values, so basically the values of the density function in all the other regions are equal to the 0. So let me integrate the kx squared dx. So this is kx cubed divided to the 3, so we need to put the values 0 and 3. So if I put the 3 to here, it will be k multiplied to the 3 multiplied to the 3 multiplied to the 3 divided to the 3 minus k multiplied to the 0 and the cube over 3, right? So this is equal to the 9k, and this should be equal to the 1, right? So that is why k is equal to the 1 over 9. So the density function is equal to 1 over 9 x squared. On the second problem B, we need to evaluate the cumulative distribution, right? So we know that the cumulative distribution until some point x is equal to the integration of the density function from 0, because the density function is non-zero in the region from 0 to the 3 until some point x, right? So I need to use a different letter for the density function. So this will be from 0 to the x 1 over 9 t squared dt, right? If I integrate this, it will be 1 over 9 multiplied to the t cubed over 3. We need to put the values from 0 to the x, and this will be x cubed over 27. So this is the cumulative distribution function for the random variable x, big X, right? And the next problem, we need to calculate the expected value of the new variable y, which is simply equal to the x cubed, right? So we need to use the formula. The expected value of some function of the x is equal to the integration of this function multiplied to the density function of the x. And we need to integrate this from minus infinity to the plus infinity, or the region where the density function is non-zero. So the expected value of the y, which is equal to the x cubed, is equal to the integration from 0 to the 3, x cubed multiplied to the density function, which is 1 over 9 x squared dx, right? So this is equal to 1 over 9 multiplied to the x in the power of 6 over 6. We need to put the values from 0 to the 3, so this will be 3 in the power of, or let me multiply 3 squared multiplied to the 3 multiplied to the 3 cubed, divided to the 9 multiplied to the 3 multiplied to the 2. So I can calculate, so divide this and this, divide this and this, so this will be 27 over 2, or 13.5. Right? So in a question number, in a D part, we need to get a formula for the variance of the y. So even though we don't need to calculate this, so the variance of the y is the expectation of the y square minus the expected value of the x in the square, or simply the expectation of the x in the power of 6, right? Because y is equal to the x in the power of 3 minus expectation of the, here should be y, sorry, expectation of the x cubed in the square. We have already calculated this, right? So the expectation of the x in the power of 6 is simply the integration from 0 to the 3 of the x in the power of 6 multiplied to the 1 over 9 x squared dx, or simply this will be 1 over 9 multiplied to the x in the power of 9 divided to the 9. So we need to put this from 0 to the 3. So this will be 3 in the power of 9, right? So I can write as 3 in the power of 2 multiplied to the 3 in the power of 2 multiplied to the 3 in the power of 5 divided to the 9 multiplied to the 9, or simply 3 in the power of 5. So the variance of the y is equal to the 3 in the power of 5 minus 13.5 in the square, right? So the last problem is a little bit tricky. So we need to get the density function of this new variable y. So we can get this using the cumulative density function, distribution function. So we need to find the density function of the y. So we can get this from the cumulative density function of this new variable. So the cumulative distribution function of the y until some y, this is equal to the probability that the random variable y is less or equal than some small y, than some fixed value y. So which is equal to the, so we don't know how to calculate this, right? Because we don't know its density function, but we know that y is equal to the x cubed, and we need to calculate the probability that x cubed is less than y. So still we don't know how to calculate this, but we know how to calculate probability of this x, random variable x, is less or equal some fixed value cubic root of the y, right? So previously we have already calculated the, so this is the cumulative distribution of the x when we need to put the value cubic root of this y, right? So we know how to calculate this already because we have already calculated the function of the cumulative distribution for this x, so which is x cubed divided to the 27, so which is cubic root of the y and the cube divided to the 27, or simply y over 27, right? So cumulative distribution function of the new variable y is equal to the y over 27, and in order to get the density function of the y, we need to simply take the derivative of the cumulative function, which will be equal to the 1 over 27. So the density function of the y is equal to the 1 over 27. Let's go to the problem number 4. In this problem, we need to evaluate the expected value of the x, so which is like pretty much straightforward. So we need to multiply each of the output to its corresponding probability and sum this at the end. So 0 multiplied to the 0.125 plus 1 multiplied to the 0.375 plus t multiplied to the 0.375 plus 3 multiplied to the 0.125. Right? So I can take out the 0.125 out of the brackets, right? So this is 0. So here I will have 3, because this is 3 multiplied to the 0.125. This is again 3 multiplied to the 0.125, right? So this will be plus 6 plus 3, which is equal to the 12 multiplied to the 0.125, which is equal to 1.5. On the next problem, we can calculate the expectation of the x plus x squared by opening up the brackets, right? So this will be expectation of the x squared plus tx, or simply the expectation of the x squared plus t multiplied to the expectation of the x. So in order to calculate the expectation of the x squared, we will square each of the outputs of the x from this table and multiply this to its corresponding probability. So this will be 0 in the square multiplied to the 0.125 plus 1 in the square multiplied to the 0.375 plus t in the square multiplied to the 0.375 plus 3 in the square multiplied to the 0.125. So which is equal to, if I take out 125 from the brackets, it will be 1 plus 4 multiplied to the 3 plus 9, which is equal to the 20t multiplied to the 0.125, which is equal to the t.75. So the expectation of the x multiplied to the x plus t is t.75 plus t multiplied to the 1.5. Problem number 7, problem number 5.